So I move to now my part of the presentation, which really is a good segue coming from Abdeen's remarks, which talked about the GWADI program. And I will try to move it forward if I know how to work this. So I wish to acknowledge that I'm at the Center for Hydrometeorology and Remote Sensing at the University of California, Irvine. And as always, we have to identify our funding agencies, which their logos are at the bottom of my slide. I used to be at the University of Arizona for 20 years, 83 to 2003. And I guess through my mission at the University of Arizona is when I became familiar with Howard's work. And he had a number of visits, and Thorsten came to us at that time. Then I moved to the University of California in Irvine, which is one of the 10 campuses of the UC system. And I do like to acknowledge some of the students and colleagues who have worked with me over the years from Arizona days. And there are many others, and sorry I couldn't accommodate everybody's pictures. So coming to our activities with Howard, we've had numerous number of GWADI planning meetings. This is the Irvine meeting, and Howard not only was a great contributor to GWADI, but was a great friend of my family members here, with, which was in a Persian restaurant, by the way. And also the meeting of 2009 that I guess Abdeen alluded to was again one of those other planning meetings that we had in Amman, Jordan. So we've heard quite a few talks about various aspects of hydrology and water resources, and at the end of the day, we are at the mercy of usually some form of modeling. So when it comes to modeling, my way of thinking about it, there are 3 parts to a successful modeling mission. One is the choice of the model and the process equations that go into it. The second one is that parameterization of it, which is in hydrology known as calibration. And finally, the data that is required to drive the model and do the calibration. And if you get them all correctly and the world was a perfect world, you would probably match it perfectly, okay? But we know watershed systems are nonlinear and too complex to model, and I think Jeff McDonald's talk, among a few other people today, highlighted that at the micro scale, things are pretty complicated and complex, and we apologize when we as modelers forget about all that details and just try to lump and do all kinds of other things that may really contribute not to the perfect match, and that's why neither the models nor the data and the parameters are perfect, and it's really how do we fill those gaps, and that's where most of the younger people are trying to work and make contributions, including the center that Howard started here. So my talk for the next few minutes is not going to be about the models and the parameter estimation. It's going to be something that GWADI made a contribution, and that's the data. So hydrometeorological purposes, we need to really, at least if nothing else, 2 main observations. Those are the precipitation and the stream flow. And Wouter already talked about some of the difficulties of in situ observations of runoff at the global scale, and not mentioning the quality of the data that you get. And precipitation, of course, is a bigger challenge. And this is a storm happening in Tucson, Arizona, when I was there during the monsoon season in the summer, which, of course, the gauge at the airport shows 0 rainfall. And this particular little canyon in the foothills of Tucson received about 2 inches in a matter of 45 minutes. And some $1 million houses, I tell you, were damaged, okay? So this is the complexity that we feel. So I'll talk a little bit about the precipitation. It's the same storm, okay, from my house in Tucson, the picture. So precipitation, in my view, is one of the key hydrometeorological challenges, particularly having high adequate resolution in time and space for model input, calibration, testing, and capturing extremes, because these days everything is about extremes. So what do we have in the way of instrumentation to measure it? Of course, rain gauge is the preferred thing for hydrologists. Then we have the radar, and after that, most recently in the past several decades, application of satellites has been explored and ongoing. So if we talk about the other two ways by which measurements are taking place, and you would consider US to have quite a bit of a sophisticated network of measuring stuff. On the right-hand side, these are the official National Weather Service rain gauges for the western United States. And if you look at the writing, it says on the average, there is 1 gauge for 600 kilometers square. So how do you capture those storms? You can imagine yourself. And the other one is radar. Of course, we have quite a sophisticated radar system deployed over the United States. And again, I focus on the western United States and the challenges it poses for radar systems. All the little pinky or bluish circles represent the whole span of the radar at 3-kilometer elevation above land. And if you look at that picture as I click, if the angle of attack of the radar is 3 kilometers, that's the coverage you have. If I click and go down 2 kilometers above the ground, you see the coverage because of the obstacles and the mountains decreases. And if I drop it another 1,000 meters, you see that the radar is totally inadequate to capture precipitation in most regions of the western United States because of the mountains. Of course, hydrologists prefer it to be at a few meters above the ground. And I don't have time to really show how different the results you would get from rain gauges we did over Arizona versus radars. So those are some of the inadequacies you see in each of these, but that doesn't mean that satellites are going to solve all the problems. They have their own challenges. But let me talk a little bit about the work that, in fact, was motivated quite a bit with respect to the activities we had in the GWADI program. The work in my group really is more to do with the IR, which is the geostationary satellites, which are about 35,000 kilometers above the Earth, synchronized with the rotation of the Earth. The second group are the passive microwave that are polar orbiting, go over one area twice a day, a snapshot, and then the TRMM was the first time it introduced an active radar in space, and now GPM has substituted that. So the key is if you want it for hydrologic applications in spatial and temporal resolutions, then you really have to also use the capabilities of the geostationary satellites, but from 35,000 kilometers, I don't care what kind of eyes you have, what kind of sensors you have, it's pretty hard to see everything. So you need to really combine all of these. So the work that started in my group back in Arizona days with Colin Hsu as a student was the introduction of machine learning tools. In those days, they didn't call them these fancy names. It was still artificial neural network. And it was essentially to take the IR information, use them through a neural network scheme, use the other satellites as a training for the nodes of the artificial neural network, and then spit out precipitation information. So that was our original work back in the 1990s. And since then, with the GPM that was launched a few years ago between US and Japan, which is the Global Precipitation Mission. In fact, the core algorithm that is used in GPM is known as iMerge, and it includes part of our algorithm for the GEOS part of it in the NASA and the NOAA, and Colin Hsu has been the PI on that, working with colleagues at NASA, and that's an operational algorithm known as iMerge. And this is pretty much the type of product you get out of iMerge every 3 hours. It updates the information. But you know flash floods can come and go within an hour, and 3 hours may not even be sufficient to capture those, particularly in the context of convections. So this is where GWADI really helped us and motivated us to work. So I will introduce under the scheme, under the PERSIANN, by the way, PERSIANN stands for Precipitation Estimation using remotely sensed information using artificial neural networks. So it's two ends over there. No confusion, since I'm from Iran, that I tried to name it after my own country, which I'm proud it would have been. But anyhow, then we have three types of products that I'd like to introduce here. One is this, known as the CHRS RainSphere, which is a real-time data product, and then RainSphere. I'll introduce these as we go in the next few minutes. CHRS RainSphere, which I call it also the GWADI, it's on the website that is serving the community, is an integrated system for global real-time precipitation estimation. Because you need the high resolution that is closer to 4 kilometers, that is the radar, it requires some special deep learning, machine learning tools to get through the clouds and classify the clouds in terms of their brightness, temperature. I won't go into too much detail. Hong Yang, who is now a professor at the University of Oklahoma, was the student who worked on this. And the papers on PERSIANN CCS are there, and that's the core algorithm that is used also in the GWADI context and in the iRain system. So it essentially classifies clouds because you need to do that in order to be able to discriminate between clouds that produce rainfall or don't. And even doing that, it's still a very challenging problem. So if you go to the website iRain, this is the type of thing you see. Every half an hour, it updates the precipitation globally. And even though GWADI was meant to be for arid regions, but it spans 60 north to 60 south, and this is what you get. Over the United States, we have integrated the gauge data real time that is available with the radar data. So this is Hurricane Harvey, okay, tropical Hurricane Harvey. And it also has the ability that you can make the comparison of how is the satellite do vis-a-vis the radar and the gauges. Not always perfect, but in the case of these massive storms, it did pretty well. I mean, you can see the comparisons that are made. And it has many features. You can click, and there's tutorials available for about 4 or 5 minutes that tells how to manipulate this website. And here is another comparisons. You can actually do a hexagonal around an area that you want, and then get the information as you wish. We do have also an app made for it, iRain, both for Android and iOS devices. And it was launched at the meeting of the parties, COP23 in Marrakesh, as a GWADI UNESCO product. Just about 6 years ago, NOAA came to us because our algorithm can go back to the early generation of geostationary satellites because it's based on brightness, temperature, and they were the first generation of satellites capturing weather to go and create a history as long as we could, and those satellites started flying from 1978, 79. And then Hamid Ashuri and Colin Shu were co-PIs on this project. This data product that we produce for NOAA, and it's sent back to NOAA and is released by NOAA from NCDC, covers the 1983 to 2016. I should update the date. Every quarter we update it. Covers 60 north to 60 south. Spatial resolution is 1/4 degree, and we are now moving toward the 4-kilometer resolution. And it was published in BAMS in 2015, January, as a cover story. And interestingly enough, in that 2 years, it's already more than 100 times cited for various applications. And it's really, really interesting to read about it. So what are the capabilities of this? I focus on Sierras. I can go to this database and actually get 35 years of the historical record on an annual basis. If I like, I can choose a single year and look at the monthly data, average over 35 years. And then if I want, I can choose a month and see what were the daily precipitations for those days. And that's really important for extreme precipitation studies. Many regional evaluations of the PERSIANN CDR have already been reported. As I said, CDR paper has been cited more than 100, and maybe about 60% of them are comparisons in various different parts of the world. So the question is, what's the value of those comparative studies? It all depends upon where you get the information to do the comparison. So most people prefer to use gauge information. My colleague, Dr. Miao, spent a year with us, and here are some of the examples. For instance, over northwestern China, you have 1 gauge per every 25,000 kilometers, and in the more monsoon region of China, 2 gauges per 10,000 kilometers square. So you're limited by the gauges that you have to do these comparisons, but yet the lowest hanging fruit, if you're really interested in publication, find a region, take a bunch of these satellite products, and do whatever apple and orange comparisons, and they get published, by the way, okay? There's no shortage of those. Rather than trying to help to solve some of the challenges of the algorithms, everybody loves to do comparisons. I'm not encouraging you students to do that, okay? So what is the value of this data set to application and modeling communities? Just one example. You've seen all the CMIP5 studies from all the climate models, and here are some of them on the top, the Chinese model, the NCAR, the UK, the Japanese model, and Germany, in terms of their retrospective 83 to 2005 projections of precipitation over Iran, okay? And here is our remotely sensed data, which says PERSIANN CDR. One of the roles that this data set has started playing is to allow people to do the comparisons, and maybe among all the 25 plus climate models, you could regionalize them and see how many of them or subset of them work better for certain regions based on retrospective data, and maybe they would be better candidates for the future as opposed to the hodgepodge of ensemble of 20 some odd models, okay? That's one example that I wanted to show, and those studies have been done. The next part of it is I already talked about the CDR data. We took the data ourselves, brought it back, and tried to make it a user-friendly product as we did for the iRain, for the GWADI program. And here is that particular website called the PERSIANN CHRS RainSphere. There are different fields by which you can customize the data that you're interested to look at it. Rainfall statistics and trends, you want to do comparisons between years, etc. Again, a nice tutorial there to allow you to, in 5 minutes, to see how you can manipulate this page. For instance, if I'm interested in the precipitation pattern with China on an annual basis, I can go there and choose my country, and it's pretty fast code. It allows you to see what trends of precipitation you see. You can go to the months and daily and so on. If you're interested in a province in China, you can do the same thing and go. You can go even to a watershed if you wish with this data set and take a look at what maybe are the trends of the precipitation. Well, there's a lot been said about global warming and its impact, and one of those is supposedly if it's warming and more ocean water evaporates, we should get more precipitation. Well, if you see from our results, and it's been confirmed by a few others later, that precipitation change over the oceans, which, by the way, data never existed now that satellites are allowed to provide you that, showed no detectable change in the past 3 decades, and neither over any of the continents. So at the larger scale, so where is all this precipitation going? Don't ask me. Maybe they go above 60 north and 60 south, but certainly over the continents, it does not show any detectable change in precipitation pattern. However, if you go into details of various countries, which again, this database allows you to do it, these are by countries, okay, the lower graph, and then on the top, I look at US for various states, and for Saudi Arabia, etc. And you can actually see that indeed, you do see detectable changes of maybe trends downward and upward, and you can do the analysis. And you can do it for a point. This is for Nevada. You can go and see if there was any trend, and you can even go to the daily or the monthly to see if there were those kinds of trends there too. And finally, major basins. For Colorado, we see detectable change of, unfortunately, negative trend in precipitation over the Colorado River Basin. We put all this data, what we call data portal. Okay, it's served. You can go there and customize what you need, all for free, thanks to GWADI and some of the other agencies that have helped us. You can get it. The question you might have is, who the hell cares who uses it? Okay, so we also have a website which says CHRS user statistics, okay? It's written on the top. And this is as of 4 or 5 days ago. We monitor who are and from which part of the world people are coming. Anything that is flashing means that people came to the site in the past 24 hours. there have been almost 715,000 as of a few days ago. As of today, I checked, it was about 720. So it grows by 1,000 a day that people come to the site. It goes by countries, 199 countries. The amount of data that is downloaded is also shown, so we keep track of you guys. But we don't know who you are. And NOAA, we asked them, because they serve the data, they finally said they could give me only a bulk estimate, but they can't give details because of privacy issues. In 2017, there was 1.6 million downloads of the data. So it's really pretty impressive and makes us happy. All this software that have been developed, no major mega funding. It's been really a shoestring operation by Professor, let me see. Okay, I better hold it in the right way. For when, and some undergraduates from computer science who are passionate to help us with this thing. That's how we've achieved all these things. Now let me just wrap up. How much trust in remotely sensed observations and model-generated data? Because at the end of the day, what's the quality of what we produce? There are pretty pictures all over the maps. These are the limitations of precipitation algorithms that at least we have. You have high-level convective storms, you have high-level cirrus-type clouds, which are cold, and you have low-level warm clouds that produce precipitation. And IR-based algorithms, unfortunately, don't capture these latter two, but they do well with the other one. Okay, so you're going to miss quite a bit or misinformed because cirrus clouds say precipitation, there is no precipitation. So that's where machine learning tools have become handy to try to include more of the new, if you wish, channels and try to overcome some of these difficulties, and that's the work that students usually do. Devils are in details. Eric Wood yesterday talked about how they merged some of the data from different places. Unfortunately, he's not here with me now, but I did tell him that be careful. He uses GPCP data. It goes back to 79. We actually decided not to use 1979 to 83 because of these kinds of things on each scene that you see. That is the foundation of the data that goes into generating the information. So we found this to be pretty contaminated with so many holes that we ignored all that. And even after that, every scene has to be examined to see how is the IR data. That is essentially the main ingredient of generating the data. So what I'm telling you is that don't believe what you see. Sometimes there is so much more in the details of it. Furthermore, we talk about remote sensing information, and we talk about model-generated information, like reanalysis data on NAR and LDAS products. This is over the California's irrigation region. We have 3 papers in JGR, and it's already expressed there. This is monthly ET values. The one thing that you notice immediately, the 2 products of the MODIS, and somebody was talking about using MODIS ET information. The same source of data used by 2 different institutions, both south of you, one University of Washington, or southwest of you, and Montana, they show different values. Okay, those are the 2 on the left. And then if you want to use any of those as an observation for ET because nothing else is available, then you want to compare it with the products that come from model-generated information, NAR, and GLDAS, and NLDAS. You see it's all over the map. So you can expect that the results of your studies will depend very much with what data you chose in order to apply. You know, other examples of sometimes you have to be careful what you see. This result was presented in a meeting in Melbourne at the GWEX conference some years ago about landslide risk maps. And as you see, red is the highest risk, yellow is the second, and then, of course, up to the blue, that is little risk. And I come from Iran, and the first thing that grabbed my eye was, my God, the whole Iran seems to be at risk 4. And I come from the desert region, and I know that big chunk of that area, the highest thing you could see is sand dunes. Okay, so I asked the gentleman, I said, how could this be at the risk of 4 of landslide? Because it's pretty flat, and it's sand dunes. Since then, of course, this has been corrected. So my point is, don't take what you see as eventual words. So have a will to doubt. Always good to question the credibility of the information reported to you. Howard, a lot of the work we did together, of course, was also had the blessing of the Vatican too. So Howard and I had the opportunity to be at Pontifical Academy of Sciences, and this was a beatification ceremony, and they each gave us a medal to be members of the Pontifical Academy in order to go to the Vatican for the celebration. Unfortunately, they collected them after that. So this is a picture of that. And this is another wonderful picture with Jim Dooch, who was with us and one of the pioneers of the hydrology. And thank you, Howard. For the many years of friendship and inspirations. Thank you.
Thank you. That was great. Questions for Soroosh with any aspects of his talk?
Yes.
Please use the microphone.
Sorry, just first time I hear about this product. There is the iRain is the one that's real time.
Real time.
And was it compared to her data, like high resolution rapid refresh used by?
To which data? I'm sorry.
The high resolution rapid refresh. That's the National Weather Service used to produce.
Okay. Well, you know, you have to be careful of what is the meaning of real-time data. There are different products that come out. Some of them are called real-time data. The raw data that is produced, and after that they wait, this CMORPH I think you're talking about. Then they have to wait for other information such as gauges to come to correct it. The actual value that they pretty much have the stamp of approval comes to you 48 hours after the storm has happened. Ours is meant to be what it is, for better or worse, because that's what happened, and every half hour we update our data. We don't necessarily recalibrate using the morphing process. We do have a product like that based on the work of Yuming Chao, who, by the way, you train these students and they never stay in hydrology. Guess where they end up? The last two, Facebook. And one of them for Uber, because it pays a lot better, and hydrology doesn't. So anyhow, that's really what it is.
It just attracted my attention that if it's compared to such, like for example, her, it would encourage more National Weather Service to use it to prepare stage 4.
You know what, we don't insist on anybody. As I told you, there's 700,000 people so far that come to the site. They download the data, and they use, and part of it is a product of NOAA, but you know, it's a free world.
Yeah, thank you.
Okay.
Thank you so much for the nice presentation. Sure. I wonder if there exists, or you're aware of, any experiments internationally that for ground truthing of some of the remote sensing precipitation products, given the huge importance of those products. Are you aware of any experiments to ground truth those products?
Well, I told you, I mean, some of these already, if you go to the literature, there are tons of, in fact, I saw a colleague here. Elvis, where are you? Elvis?
Elvis? Here?
Elvis, where are you? Elvis said he did a comparison, so I don't know. You know.
No, I meant like huge organizations like NASA designing networks of rain gauges and those kind of things.
No, there is some networks that NASA created for the TRIM mission for validation sites. Unfortunately, I don't think they were as successful. But now under GPM, there is a different network. So it's time. You have to allow it for them to produce this. But, you know, our product, I mean, regionally people apply in different places, right? Some say it's the greatest thing ever, and some say it's the worst thing ever. And if you go to each one of them, either the great or the good, they're mostly comparisons of apples and oranges because they don't necessarily have the same features. Sometimes they aggregate, disaggregate in strange ways, and that's why there are so many journals. They love to get stuff to publish and have you pay for it.
All right, thank you.
Okay, thank you again.